Let's look at some practice IR spectra. So here we have three molecules, a carboxylic acid, an alcohol, and an amine. And below there's an IR spectrum of one of these molecules. So let's figure out which molecule has this IR spectrum. So we could draw a line around 1500 and ignore the stuff to the right and focus in on the diagnostic region. And in here is your double bond region, and I don't see a signal at all in the double bond region. I certainly don't see a very strong carbonyl stretch, and so the carboxylic acid is out, right? So I don't see any kind of a carbonyl stretch in here. We do see some signals over here to the left in the bond to hydrogen region. And so I could draw a line about 3000, and I know below that we're talking about a carbon-hydrogen bond stretch where you have an sp3 hybridized carbon. That doesn't help us out here at all, but this other signal does, right? So we have another signal, so it's centered on a higher wave number, and it's extremely broad. So whenever you see that, you should think to yourself hydrogen bonding, and this is due to an OH bond stretch. So immediately we know that we must be talking about an alcohol here. A carboxylic acid has a similar OH bond stretch, right? So it has a broad signal due to that, but there's no carbonyl, so it couldn't possibly be this molecule. It also couldn't possibly be the amine, because even though we have nitrogen-hydrogen bond, right? A nitrogen-hydrogen bond stretch is going to be in a similar region, right? We would expect two signals for this. We would expect a symmetric stretch signal and an asymmetric stretching signal, and it wouldn't be as broad as what we're talking about here for the alcohol. So it's definitely not the amine. So this spectrum is the alcohol. Let's look at three more molecules and a different spectrum, right? So let's look at the spectrum here. We start with 1500, right? So we draw a line here. We look in the double bond region, right? So here's our double bond region. I do see a signal this time, and it doesn't look like it's a very strong signal either. Let's see what the location of this signal is. So I drop down, and the signal shows up between 1600 and 1700. So we'll say approximately 1650. That's not very strong. Both of those things, the location, right, and the fact that it's not a very strong signal, clue me into the fact that this is probably a carbon-carbon double bond stretch. That's what this is talking about here. Right, so a carbonyl, we would expect that to be just past 1700 and also much, much stronger. So we can rule out this molecule over here because I don't see any kind of a carbonyl stretch. Right, so let's look in the triple bond region. So somewhere in here, I don't see any kind of a signal. So it couldn't possibly be this molecule. So we must be talking about cyclohexene here. And if we look over in the bond to hydrogen region and we draw a line, right, we can see that this signal, right, just higher than 3000, this must be talking about our carbon-hydrogen bond stretch where the carbon is sp2 hybridized, right? So this is of course talking about our carbon-hydrogen stretch where we're talking about an sp3 hybridized carbon. And so cyclohexene is the only thing that makes sense with this IR spectrum. Let's do one more. So we have three molecules and an IR spectrum. All right, so let's start analyzing. Draw our line around 1500 right here. Focus in to the left of that line. And this is our double bond region. So two clear signals in the double bond region. Let's look at this signal right here, right? So it's not as intense as the other one, and it's pretty much between 1600 and 1700. So both those factors make me think carbon-carbon double bond stretch, right? So this is probably a carbon-carbon double bond stretch here. The signal next to it, right, if this is 1600, this is 1700, so this signal is just past 1700, and it's very strong, right? It's a very strong signal. So that makes me think carbonyl, right? So this makes me think carbonyl right here. So we can immediately rule out this one, right? So it couldn't possibly be that molecule. And that brings us to this, which is a conjugated ketone versus an unconjugated ketone. All right, so let's think about the unconjugated ketone for a minute here. So this carbonyl stretch, we talked about in an earlier video, we'd expect to find that somewhere around 1715, so past 1700. right? This ketone over here, this conjugated ketone, right, we have resonance, and we know what resonance does to the carbonyl, right? So it decreases the strength of the carbonyl, and therefore it decreases the force constant K. That decreases the frequency of vibration, and we would expect this carbonyl signal to have a lower wave number than 1715. Actually, it moves it under 1700 to somewhere around 1680 is where we would expect it to be. I don't know exactly where it is, but it's definitely less than 1700, and this is very clearly, let me go ahead and mark this here, this is very clearly the 1700 line, and our signal is past that. So this must be talking about the unconjugated ketone over here on the right, and so this spectrum corresponds to this molecule. So hopefully that gives you a little bit of insight into how to approach some simple IR spectra.